Hello everyone, my name is Fanizza Tahir. You guys probably know me as Azir on Discord, and today we're going to dive into the topic of quantum transpiler services. This topic is crucial in quantum computing as it serves as a bridge between quantum algorithms and the actual hardware needed to run them. I'm super excited to walk you through what transpilers are, how they work, and why they matter in the quantum world. By the end of this presentation, you'll not only understand what a quantum transpiler does, but also appreciate how vital they are when it comes to quantum computing. Now, let's get started. First, let's start off with the basics. What exactly is a transpiler? Well, a transpiler is a source-to-source compiler that translates code from one programming language into another. To help you understand further, I'll give you an analogy. Imagine working in a company where every computer system speaks a different language. If you write a program in Python, but your computer only understands Java, you would need something to translate that code. That's where transpilers come in. They act as the translators in quantum computing, ensuring that algorithms written in one language can be understood and executed by different quantum devices. I know that I just mentioned that a transpiler is a source-to-source compiler, and you may be wondering to yourself, if a transpiler converts code from one language to another, then it's just a normal compiler. Even though I've mentioned that it's a compiler, transpilers and compilers are actually two different things. The main difference between a compiler and a transpiler is that a compiler converts code into instructions that are often executable by machines, whereas transpilers focuses on making code compatible across different computer systems or optimizing it for specific use cases. To simplify this, a compiler runs code while transpilers translate code. The transpiler acts like a chef converting a French recipe into one that can be cooked in an American kitchen, adjusting the tools and ingredients while keeping the dish intact. The same applies to translating the quantum literacy program from English to Spanish. Everything remains the same, but the languages change. Similarly, in quantum computing, transpilers often adapt algorithms so that they can run on various quantum devices, all while maintaining their original intent. I want to clarify that transpilers are not quantum programs, but classical programs. They run on classical computers but often operate on quantum circuits, which are algorithms designed for quantum hardware. This classical quantum bridge is what makes transpilers so special. While they function in the classical realm, their output significantly impacts how quantum circuits operate on actual hardware. Now, let's take a deeper dive at how a transpiler works. Now, let's take a look at how quantum transpilers work, and we'll use Qiskit's OpenKSM as an example. On the left-hand side, you'll see a screenshot of an algorithm written in OpenKSM. It's basically just a simple quantum transpiler. And on the right side, we have a step-by-step breakdown of the algorithm. Now, I'll walk you through on how this transpiler works step by step. So the first thing you need to do is declare our registers. This is like setting up containers to hold both quantum and classical bits. You need to include the header and libraries, OpenKSM 2.0 and QElib1.inc in order for this to work. Then you need to declare quantum and classical registers with 2 qubits, QREG-Q2 and CREG-Q2. After that, we need to apply the Hadamard gate to the first qubit HQ0. Applying that Hadamard gate will put the qubit into superposition. This is a fundamental quantum concept where the qubit can be both 0 and 1 at the same time. After that, we need to apply the CNOT gate EXQ0Q1. This introduces entanglement between the qubits. This is also another unique quantum phenomenon where the state of one qubit depends on the state of another. And last but not least, we need to measure the qubits and store the result measure Q arrow C semicolon. At this stage, the code is hardware independent. This means that it could run on various quantum devices. However, different devices have their own constraints, like which gates they support, or how qubits are connected. The transpiler adjusts this high-level circuit for the hardware, which often ensures that it would run optimally. Think of the transpiler as a team of engineers redesigning a blueprint of a bridge in order to fit that specific bridge to a landscape. Without that adjustment, the bridge wouldn't be safe or functional. In quantum computing, circuits need similar adjustments in order for it to work and adapt to the area around them. Now, I'll walk you through on how a transpiler works before and after the process of transpilation. So here we can see the same circuit before and after transpilation. So before transpilation happens, the circuit is considered inefficient because some qubits interact in ways that might not work well on a particular quantum processor. For example, certain quantum hardware can't handle specific gate combinations directly. Running such a circuit would introduce errors and inefficiencies. On the left-hand side of the slide, we can see a quantum circuit before transpilation. It is not optimized and might be incompatible with some quantum processors due to mismatched gates or poor qubit routing. So I'll show you what the algorithm looked like before transpilation. So before transpilation, we needed to include the headers in libraries OpenKSM 2.0 and QElib1inc. Then what we need to do is we needed to declare quantum and classical registers with 3 qubits, QReg3 and CReg-C3. Then what we need to do is we needed to apply the Hadamard gate to the first qubit, HQ0. Then we needed to apply the CNOT gate, EXQ0Q1 semicolon, then CXQ0Q2. Then we needed to measure the qubits and store the result measure Q arrow sign C semicolon. So the picture in the middle shows a quantum circuit after transpilation. After transpilation, the circuit becomes optimized as the number of gates have been reduced and the operations have been recognized. This is so that the quantum computers are able to execute the algorithm faster, with fewer errors and less noise. After transpilation, the circuit has been optimized for hardware-specific requirements, reducing in fewer gates, reduced errors, and faster processing. To help you guys further understand transpilation, let's imagine that you're building a house. Before optimization, you might have a staircase in a place that blocks a doorway or windows that don't align with the rooms. After optimization, everything flows smoothly as the doors, stairs, and windows are placed in a way that makes the house more functional. Now, I'm going to talk about the benefits of quantum transpilers. So, the benefits of quantum transpilers. You see, there are 3 specific benefits that quantum transpilers have. The first benefit is circuit optimization. So, as we've seen throughout this presentation, transpilers simplify circuits by reducing unnecessary gates. This improves the overall performance and algorithm on a quantum computer. Then, the second one is error reduction. Quantum computers are prone to noise and decoherence, which can disrupt the computation. Transpilers help by recognizing operations and reorganizing it. This is so that it can minimize these errors, which often ensures that computation runs smoothly. And last but not least, hardware compatibility. Different quantum computers have different architectures and gate sets. Without a transpiler, the same quantum algorithm might not run across all devices. Transpilers make it possible to adapt the algorithm for different hardware. Now I'll talk about the challenges of quantum transpilers. Even though quantum transpilers offer significant advantages, they also face several challenges. So, the main challenges that come with quantum transpilers are limited qubit connectivity, quantum decoherence, and noise. So the first one I'll go through is limited qubit connectivity. So not all qubits in a quantum computer can interact with each other. The transpiler has to figure out how to route the qubits in a way that avoids these limitations, which can add extra complexity and gates to the circuit. As for quantum decoherence, quantum states are extremely delicate. Decoherence causes them to lose their quantum properties over time, and even optimized circuits are susceptible to this. Transpilers need to minimize the time that qubits spend in vulnerable states. And last but not least, noise. quantum gates introduce noise, which can often cause distortions in computations. While transpilers work to reduce this, noise is still a significant hurdle in making quantum computing accurate and reliable. These challenges often show that while transpilers are essential, there are still lots of work to be done in overcoming the limitations of today's quantum systems. Although transpilers are classical programs, they must optimize circuits with quantum-specific challenges in mind. Think of them as classical tools navigating quantum realities, optimizing circuits while considering the effects of the quantum environment. So before I move on to the next slide, I'm going to tell you guys a short story of why I believe quantum transpilers should be used before trying to run anything on your computer. So I was in this quantum summer program back in July, and my friend needed help with his final project. The thing is, his final project was coded in a way so that his computer can run it. He wanted me to run it on an NVIDIA PC, which is what I had at the time. And I thought it would work because he told me so much about how his project would work on an NVIDIA computer. So what I did is I looked at a project. It was on Google Colab instead of Anaconda Navigator. And I thought it was going to work well on my computer. After trying to run it for an hour, my computer crashed. At first, I thought that there was just an issue with my Wi-Fi, until I realized that the reason why my computer crashed was because it was unable to run any of the code my friend wrote. The code that he wrote was written in a way so that only his computer can run it. Like, when I was looking through the code, I saw that all the circuits and all of the quantum algorithms were coded in a way so that only his 2009 HP laptop can run it. This made me realize that without transpilers, my computer had to go through an issue. When it comes to quantum computing altogether, your computer will not be able to run anything without it going through transpilation first. Based on my story, I learned that transpilation is necessary in order for quantum algorithms to adapt onto new systems. Because the algorithm my friend coded was made for his computer, I wasn't able to run it on mine. And the algorithm was only made to run on his. Now I'm going to talk about the future of transpilers and how quantum transpilers can impact fields around the world. So looking into the future, AI-driven quantum transpilers could significantly improve optimization. Machine learning models can adapt circuits based on past performance, while reinforcement learning algorithms can continuously learn from execution feedback to enhance their strategies. When it comes to machine learning, AI can analyze past transpilation tasks to identify patterns that can lead to better circuit optimization. Imagine an AI that knows the best way to configure a quantum circuit because it has learned from thousands of previous circuits, making it informed decisions that reduce errors and increase efficiency. And when it comes to reinforcement learning, AI models can improve over time through trial and error. After each circuit execution, the AI receives feedback, which allows it to adapt a strategy and refine its approach, leading to increasingly efficient transpilation processes. These advancements could revolutionize fields like cryptography, where Shor's algorithm is used for factoring large numbers. AI-driven transpilers could optimize this algorithm to break encryption more efficiently, providing new capabilities for secure communications. Additionally, applications in finance, drug discovery, and quantum chemistry could benefit from these AI advancements, allowing for more complex simulations and faster computational analysis. So let's talk more about the real-world applications of transpilers. Now, let's talk about some real-world applications of quantum transpilers. So when it comes to quantum transpilers, they could be used in 3 specific fields: cryptography, drug discovery, and finance modeling. As we mentioned earlier, for cryptography, Shor's algorithm can factor large numbers and potentially break encryption. However, it requires optimized circuits to run on quantum computers, and that's where transpilers come in. As for drugs discovery, quantum computers can simulate chemical reactions at quantum levels, something classical computers struggle with. Transpilers help ensure that these complex situations and simulations run effectively on quantum hardware. And for financial modeling, quantum algorithms have the potential to improve financial models by optimizing risk analysis and portfolio management. With transpilers, these algorithms can be executed more efficiently, making quantum computing more practical for finance. Each of these fields require reliance on quantum transpilers in order to unlock the potential of quantum computing. So in conclusion, quantum transpilers are crucial for optimizing circuits, making sure that quantum algorithms run well on different quantum devices. Even though they are classical tools, they play a big role in dealing with real-world issues like noise, qubit connectivity, and decoherence. Looking ahead, adding AI could make transpilation even better, leading to faster and more flexible quantum algorithms. This could help quantum computing tackle some of the world's toughest problems. Thank you for your attention today. Feel free to ask questions by pinging my name, Fanizza Tahir, on Discord. Have a great rest of your night.